Okay. We're going to start today talking about spectroscopy in the first roughly 50 minutes or so. And you've got the handouts. I will always give you the PowerPoint notes from the handouts that I give you. And then I'm trying to make it so that every week there'll be some problems to kind of reinforce what you've done. And there's a problem set that'll be due for next week that it'll be clear. It's going to be pretty straightforward. So in terms of spectroscopy, what I want to do today is kind of lay out what we need to know about spectroscopy, and then we'll talk about infrared, which I can do in one lecture. So for each of the techniques, there's going to be a reading assignment. There's one from the Smith text that we're using this year, and then there's one from the Wade text from previous years, depending on what book you have. And so infrared spectroscopy is in chapter 13 of this of the newer text, and then it's in chapter 12. And it looks like there's more reading, but there isn't, because it's the same stuff, only they broke it up a little bit more in depth. So organic spectroscopy consists of basically 4 techniques that we're going to talk about, some in depth, some not so much. So right now we've learned some organic reactions, many organic reactions, well, not as many as you'll know by the end of the year. And one of the issues that we have with determining the products is, how do you know what product you got? If you know about the Zaitsev rule, that you make the alkene that's most substituted, how did Zaitsev know that was the product that he got? How does Markovnikov know what product that you get when you add like HCl to a double bond? And how do you determine the structures of molecules that are basically brand new, or molecules that you just don't, know anything about? It's not like somebody would walk up to you on the street and say, hey, here's an organic molecule, figure out what it is. On the other hand, you could go to a tree bark or some sea urchin or a coral or something and find a unique molecule that maybe you need to know the structure of because it has some anti-tumor, anti-cancer, anti-AIDS activity. And so how do we determine the structures of those types of molecules? Here's a perfect example, Taxol. Okay, when I first started here 15 years ago, Taxol was just starting clinical trials for ovarian cancer. Now I think it's been approved, it's a commonly used drug, and it's probably being studied for other things. Notice it's pretty complicated. And there's lots of chiral centers in the molecule, which means that basically only one of the enantiomers is going to be active, one of the diastereomers. So somehow this molecule has shown a pretty good anti-tumor activity, enough to be used for ovarian cancer. But where did it come from? Well, it was originally discovered from the bark of the California yew tree, which is some little scrubby tree that doesn't grow in California, it grows in Oregon. And nobody really paid that much attention to it, but back in the 70s and early 80s, the National Institutes of Health had a program where people were encouraged to try and find novel molecules from natural sources. It's sometimes called natural products chemistry. So they took this tree bark, found it had anti-tumor activity, kept separating the compounds until they found the one compound that had the anti-tumor activity, and it was Taxol. So how did they get the structure? Because you need the structure in order to be able to make the compound, because there's not enough yew tree bark, and you don't get enough drug from the yew tree bark to make enough drug to treat ovarian cancer or anything else. And so that's where Taxol came from, where its structure came from, is the most direct and most absolute way to determine an organic structure. Not something we're going to talk about, but I'm just going to introduce it because you've seen it in all your biology books. You've seen the results of this. And that's X-ray crystallography. Somebody took the Taxol molecule and they cooled it very slowly, allowed it to precipitate, incredibly slowly, and they got what is called a single perfect crystal of it. That's a crystal that is translucent. It has a perfect shape to it. All of the atoms are perfectly arranged in that crystal. And back in general chemistry, you probably talked about body-centered cubes and face-centered cubes and the structures, the repeating structures that go with that. Well, in organic molecules, you could think about an organic solid as taking a model that you would make from the Tinker Toy models, drop it in a shoebox, and then take other shoe boxes that have the molecule in exactly the same positions and stack them on top of each other to make a three-dimensional crystal. That's the type of order we're talking about. We don't make single crystals very often in the lab. Number one, we don't have any intention to do that, but we cool things quickly. We get powders, we get oils, we get liquids. So if we were to cool these things really slowly, we would get a nice, perfect crystal. Well, perfect crystals will diffract an X-ray beam, so that when you pass an X-ray beam through a crystal, that beam gets diffracted into all sorts of beams that go off in 3 dimensions, and they have different intensities. And then using the mathematics of trying to figure out the intensity of the beam and where it is in 3-dimensional space, you can put that all back together again and get the structure of the molecule, the exact structure of the molecule. And if you have a really high-quality crystal, you can even determine whether the molecule is R or S. That's where R and S determinations ultimately come from. And there's been a number of drugs through the years that have been thought to be one chiral center configuration, and when the high-quality X-ray crystallography gets done, they find out through all those years that they were actually wrong. It was the other configuration. So we don't have the ability to do that here. We have what's called a powder diffraction instrument, but places like Case, Youngstown State has a couple of these instruments, and so sometimes I'll send crystals down there to have their structures done. I did this for 2 years as a postdoc, nearly 20 years ago when I was at Brown. And basically what happens is that you take the crystal's no more than a millimeter wide for a normal organic molecule, and you put it on the end of a glass fiber. The X-ray beam passes through it, and nowadays there's what's called a CCD camera that collects all of those images. When I was doing this, we had a single detector that had to move in all 3 dimensions, so it might take a couple days to get a crystal structure out. Nowadays, I've dropped crystals off at Youngstown State and headed to Western Pennsylvania, and when I've gotten where I've needed to go, I open up my computer and there's a structure on the screen because it's been done that quickly. Now, X-ray crystallography is not just for organic molecules, but it gives you something like this, the exact structure. Okay, this is one from an undergraduate research student that worked with me. These are the organic. You can see they're a 6-membered ring. Those are benzene rings. And then you've got a carbon-carbon double bond here because you can see the molecule's planar. And then there's some oxygens. There's actually lithiums in here. But you can get the exact 3-dimensional structure and the exact structure of the molecule from X-ray crystallography. And then if you want to see what the structure really looks like, think of taking that model and now all of a sudden stacking it up on top of each other. That's really what a solid looks like. And it's just all of those things kind of stacked together, but very regularly. Now, you've seen the results of X-ray crystallography if you've taken any biology class, or even if you haven't taken biology. This is DNA. How was the structure of DNA determined? X-ray crystallography by Watson and Crick. That's how they determined the structure of it. And bioorganic or biochemical crystallography is much more complicated because there's a lot more atoms, and the crystals tend to be smaller and harder to get. But when you see protein structures in your genetics or your biochemistry or your general bio, textbook or you see the structure of an enzyme or RNA or DNA, chances are it came from X-ray crystallography. And so there's people that just do or try and get the structures of proteins. This, I think, has some other molecule stuck to the protein or stuck to the enzyme. So with drug interactions with these molecules, these are where all these colorful pictures come from. And then, of course, because the individual atoms are sometimes too small to see, that's where you see the ribbons and the twists and all of that other stuff. But it comes from X-ray crystallography. When the space station first started to be built and the space shuttle, people were saying, oh, we can grow these perfect crystals in space because there's no gravity. And if we can grow these perfect crystals, then we can get more information about the biomolecules. And so that was one of the pushes, or one of the reasons that was given, at least, for trying to grow these in space. This is the most absolute way of getting the X-ray structure, or getting the X-ray structure is the most absolute way of getting a structure of an organic molecule, but it's not going to be very helpful to us. Because when we get organic molecules, sometimes they're oils, sometimes they're liquids, sometimes they're powders. And so do we have techniques to get the structure of those organic molecules? And the answer is yes. What we have are what are called complementary techniques, meaning that each technique gives one piece of the puzzle that we can then put together to get the structure. And the nice thing is that for some of these techniques, you can get away with 10 to 100 milligrams. If you're using something like mass spectrometry, which is used for drug testing, you're looking for sometimes nanograms of materials, and even less. So we can get structures of very small amounts of material, which is useful because let's say that I go, there's a lot of natural products chemistry that goes on in places like Hawaii, because you can go out and you can like scuba dive and you can like pick up a sea urchin and see if that sea urchin has any anti-tumor chemicals in it. Well, unfortunately for the sea urchin, the only way to get those out is to put the sea urchin in a blender. And then you get all of the different molecules from that, and then you figure out if it has anti-tumor activity. If it does, you need to figure out the structure before you can synthesize it. So you're not going to get very much out of a single sea urchin, and you're not going to be able to comb the ocean floor and get tons of these. As a matter of fact, in some cases, you can only get small pieces of coral. And there's a lot, like in Australia, there's people, that's all they study is natural products, and they have databases of all these things that come from all these different places in the ocean. And when something is biologically active and it kills tumor cells and only tumor cells, then it's something that they want to know the structure of. Sometimes you can get by X-ray, sometimes you can't. So what do you use? Well, we'll talk about ultraviolet and visible spectroscopy. You've already used UV spectroscopy, you use the visible part. General chemistry, if you measure the absorbance of a solution that has a color, you've used visible spectroscopy. What we're going to talk about is a little bit more how the molecule has a color. What makes the molecule red or blue. So we'll talk a little bit about that. And then today we'll talk about infrared. Infrared spectroscopy was one of the first ones that was available, and we use it to identify functional groups. So I can tell you whether you have an alcohol in your molecule, or an alkene, or a carbonyl, or a benzene ring by doing infrared. And then there's mass spectrometry that is used to get the molecular weight of a molecule and also the identification of it. If you watch any forensic shows, whether they're made up, like all the CSIs, or Crossing Jordan, which isn't on anymore, or what's the other one, NCIS, or there's so many of them out there. The ones that aren't real versus the ones on court TV that are real, you'll oftentimes hear about the GC mass spectrometer, which is like the tool that everybody uses to solve everything besides DNA. Well, the mass spectrometer can actually be used to identify the structures of molecules. And we'll talk about how that's done. And so that part is real. A lot of the other stuff is, the time it takes is not real on TV, and they take liberties with how easy it is to get structures. But we'll talk about mass spectrometry. And then we'll spend most of our time talking about nuclear magnetic resonance, which is, we'll talk about just the beginnings of this technique, but this is an incredibly powerful technique that lets us look at the carbon and hydrogen nuclei in a molecule. And it is an organic molecule made up of anything other than carbon and hydrogen. I mean, yeah, it's got a few oxygens and nitrogens thrown in, but for the most part, carbon and hydrogen is the bulk of it. So we'll spend a lot more time talking about NMR. But today what we want to talk about is just an introduction to the idea of electromagnetic radiation, because that's the basis of any kind of spectroscopy. And then we'll talk about the infrared and how you interpret an infrared. So, for the electromagnetic radiation spectrum, there is a whole variety of different types of electromagnetic radiation. They have different wavelengths, they have different frequencies, and because of the Planck equation, you have the energy. Remember, the energy is proportional to frequency. Right? There's the Planck's constant, so E equals h nu. So each one of these types of electromagnetic radiation has a different energy. Radio waves, microwaves, the infrared region. The visible region is a very small portion of the electromagnetic spectrum. We see just a very small amount of the color of light. That's within the visible region. Then the UVs, then the X-rays and gamma rays. So we're going to use radio waves for NMR, infrared for infrared, and visible and UV for visible and UV. Mass spectroscopy, that's an incorrect way of saying it. It's mass spectrometry. And I use the two interchangeably until somebody corrects me, like a mass spectrometrist. Be like, you know, that's wrong. And I'm like, yeah, I know, but why stop a bad habit? So mass spectrometry doesn't use light. It's a different type of technique. So when we look at a molecule, spectroscopy is based on one thing, and that is the difference in energy between the excited state and the ground state. So if you have an electron in the ground state, well, that's okay. I can record it without writing. If you have a molecule in the ground state, it absorbs energy to go into the excited state. Bless you. The energy difference is always quantized, meaning that there's a very discrete difference in those energies of those two states. Well, since energy of a photon is directly proportional to the frequency, that means that there will be a photon of one and only one frequency that can be absorbed by the molecule to go to its excited state. If the energy wasn't quantized, then it wouldn't be a single photon. So the idea is that if you have a molecule in the ground state, it will only absorb photons of that specific energy to jump up to the excited state. That's it. If it's a photon of any other energy, then it just simply will go through the molecule or it won't be absorbed. So the idea here is that if we wanted to make a molecule, or if we want to make a spectrophotometer, we just need four things. We need a light source that has our different wavelengths and frequencies of light that can be absorbed by the molecule. We need something to select a particular wavelength to pass through the sample. And so that can either be a prism or a monochromator or a grating. If you've ever taken a CD and held it up to the light, You can adjust it at an angle where you see the rainbow of colors. A CD is basically a grating. And so if you have that, you can angle the CD so that the red light passes through versus the blue versus the yellow. And so you can separate the individual wavelengths of light and pass each one through the sample one at a time. We need a sample, and then we need a detector. And so the detector will allow us to detect how much light is absorbed by the sample. And you know from general chemistry, you normally run a blank that tells you how much light passes through without the sample, and then by difference you can figure out how much light is absorbed by the sample, and you can get into percent transmittance or absorbance, all the stuff you did back in general chemistry. What we're going to do that's a little different than what you've done before is that we're going to look at a spectrum. In other words, I'm going to pass individual wavelengths of light through the sample, and I'm going to measure the corresponding absorbance by that molecule. And so what I'm going to end up with is I'm going to end up with peaks. The peaks show us what wavelength was absorbed by the molecule. And depending upon the technique, the peak may be really narrow or it may be really broad. It depends. In general chemistry, what you did was you passed a particular wavelength of light through the sample, and then you had the wavelength, you measured the absorbance, and you plotted absorbance versus concentration and got a straight line and used it quantitatively. If you took analytical, or if you're taking analytical, it'll end up the same way. You use the quantitative aspect of this. We're going to look at the position of the absorbance peak to tell us something about the structure. And so all the spectroscopy techniques will involve some sort of scanning through the light and measuring the corresponding absorbance and looking at a spectrum. Okay, so the peak and the peak position is what we're looking at. You measured the intensity and how the intensity varied as a function of concentration. That will work with all of our techniques. The intensity will change as a function of concentration, but we're going to look more at the structural aspect of it. All right, so let's get to infrared. The infrared radiation is a spectrum, part of the spectrum that has a wavelength from 2.5 times 10 to the minus third to 2.5 times 10 to the minus fourth wave numbers, or centimeters. Now, what we normally use as our x-axis in our infrared spectrum is not the centimeters, not the wavelength, but we actually use what are called reciprocal centimeters. We use what's called the wave number. And so we divide the wavelength, we put the wavelength, well, 1 divided by the wavelength, and we get reciprocal centimeters, which we call wave numbers. That's traditionally how it's been done. It's been 20, 30 years since anyone's used microns as the wavelength to make the measurement. So we're going to always talk about wave numbers, which is just reciprocal centimeters. So how does a molecule absorb infrared light? Well, basically what we have to deal with are the motions of the molecule. And a motion of the molecule has to occur at the same frequency as infrared radiation in order for the molecule to absorb. So let's take a diatomic molecule as an example. With a diatomic molecule, you have two atoms, let's say they're attached by a spring. Unless the molecule is at absolute zero, the molecule is going to vibrate back and forth as if it was attached by a spring. That vibration, that molecular vibration, occurs in the infrared frequency. In other words, infrared light has the exact same frequency as that vibration. So that when the molecule gets hit with infrared radiation of that exact frequency, it absorbs it. And we see a peak on our spectrum. If the frequency doesn't match up with the vibrational frequency, no absorption. So there's a lot of different vibrational frequencies and some rocking and some other things that I'll show you. Those frequencies are all in the infrared, and that's when the molecule will start to absorb. And when it does absorb, it just stretches the bond farther apart. So the molecule might be vibrating, and then all of a sudden when it absorbs the energy, it vibrates farther apart, but still at the same frequency. The extreme to this is if you hit it with enough energy where it would vibrate so violently that it would fly apart. We're not doing that at all. And the way we make this measurement is using what's called an infrared spectrometer. Basically, we need a source of infrared radiation. That turns out to be a glowing wire. If you've ever seen an infrared heating lamp that's used, I don't know, to keep reptiles hot, might be a place where you would see it. Sometimes in hotels, they'll put an infrared lamp above the shower so that when you step out of the shower, you feel this warmth, which is the infrared light coming down. You know, at the fast food places, they'll use infrared lamps to keep the food hot. So you just need an infrared source. Then you pass the infrared source through the sample. Sometimes you'll pass it through a reference as well. And then it goes on to what's called a monochromator, so we can select what particular wavelength we want to pass through the sample. And then it goes to the detector, and we create a chart. Now, the spectrum for an infrared is upside down. The peaks are pointing down. So this is our baseline. That's the zero absorption. And then the peaks are pointed down. That's how it's been done traditionally. And every textbook shows those peaks upside down, and so I'm going to continue doing that. We could, with the computerized instrument, we can now flip everything right side up. But nobody does. It's always still upside down. So the spectrum will usually go from about 4,000 wave numbers to about 600 is the spectrum. And you'll see that when you look at some example spectra. That's what we look at. There's other parts of the infrared region that we don't have the instruments for, like Raman and some other near-infrared techniques, but we're just going to deal with the straight organic infrared. So that's how the instrument kind of is laid out. Now, let's see if this works. I have a program called the IR Tutor that will show a little bit of how these molecules absorb with animations. So if I have my diatomic molecule is vibrating back and forth, and so it's that vibrational frequency that then is in the infrared region. And each diatomic molecule would have a slightly different frequency so that you could excite it using different wavelengths of light. And if they're really big, they don't vibrate as fast. If they're really small, they vibrate faster or whatever. What we're interested in then is to make those, as those molecules absorb their infrared radiation of that particular frequency, you end up with this peak. You end up with a peak on the infrared spectrum right here, which then tells you basically what the vibrational frequency was. The position of the peak on that spectrum is going to tell us which functional group I have, because the different functional groups have different vibrational frequencies. Okay, so that's the basic setup for this. So it's kind of hard to see, but here's the example of the molecule. There's kind of a red light wave passing through it. If the frequency of that wave matches up with that vibrational frequency, that's when you'll get the absorption. If they don't match up, they aren't going to, it's not going to absorb. And so what we do is we then scan through are different frequencies. There's an HBr molecule, so it's got a different vibrational frequency. Now, when we look at organic molecules, we look at them like this. They are like the dancing molecules. Now, a water molecule, if we grabbed its oxygen and didn't let it move, that's what it would do. Realize that a water molecule is moving in 3 dimensions. It's rotating around. But these are just its vibrational motions. And we can actually break that down into 3 different motions that it has. Okay? It has stretching and bending. The top one is a bending motion. And so the HOH bond angle is changing, it's bending. Then the other two, this is called a symmetric stretch, and the bottom one is an asymmetric stretch. Okay, and these models do a much better job than I can with my hands, which is why I bought this program. Because otherwise I have to do this, and it doesn't accomplish anything. So those are the 3 frequencies for water. And they all turn out to be in the infrared region. So if we looked at each one of those motions, they show up at different positions on our infrared spectrum. The 2 stretches, the symmetric and asymmetric stretch, show about 3,400, 3,500 wave numbers, and the bending motion shows up about, I think that's 16 or 1,400. So this motion is what we're going to be measuring. And so water absorbs infrared radiation. And if you've taken any kind of ecology class, well, you know that. The number 1 greenhouse gas is not CO2, it's water vapor. And so water absorbs infrared radiation, and it creates the climate that we have here on Earth. Change the water vapor, and you can change a lot of the climate as well. So, and when you step underneath the infrared lamp from the shower, that's what's happening, is the water molecules are absorbing the energy from the infrared. So, another infrared active molecule is CO2. CO2 is also responsible for the greenhouse effect on Earth, which is good in the fact that we're not Mars or Venus, and we actually don't go from minus 350 degrees up to 350 degrees during the day. Our climate is moderate, but you've all seen the movies and stuff about global warming, so I'm not going to get into that. But CO2 absorbs infrared radiation. And here's all the different motions that we have there. The top motion is a bending motion, and so it is infrared, what we call active. There is also the one that's the second one that you can't see. It's going like this in and out of the plane, so it's coming towards you and behind you. Then the other ones are bends, so stretches, symmetrical stretch and asymmetrical stretch. It turns out that 3 of those are actually infrared active. A molecule has to change its dipole moment in order to be infrared active. And so the third one down, where the molecule stretches symmetrically, that doesn't change the dipole of the molecule, because the 2 individual bond dipoles, if they're both moving at the same rate, they don't change. And so the third one is not active, and so you only see the other 2 at different frequencies. If you take your car to have some sort of emissions check, in Ohio, e-check, and I think in certain parts of western Pennsylvania there's an e-check system as well. They'll check it for the amount of CO2 that comes out of your car. Now, if you have an older car where they actually have to take the thing and stick it in the tailpipe, they use infrared radiation to measure the amount of CO2 that's coming out of the car. And so it's a relatively easy measurement to make, because CO2 absorbs infrared radiation, and specifically you'd look at the wavelengths of those 2 peaks. And you could create a Beer's law calibration, and you could get the CO2 concentration very easily. Now, when we get to an organic molecule, we have other types of motions that are not simple by any stretch of the imagination. And so we have different types of bending and stretching frequencies that will show up all across the spectrum at different positions. And so let's look at that. Now you have copies of the spectra. I'm going to show you. They don't dance, but they have like the different important frequencies on them. So let's deal with an alkane first. So here's the infrared spectrum of hexane. You can see that for hexane and basically for any of the alkanes, it's a pretty boring spectrum. There's only a few intense peaks. And remember, the peaks are upside down in our spectrum. But these types of frequencies turn out to be different types of stretching and bending motions. So one of them is an asymmetric stretch of a CH2. Or then there is a symmetric version of this, where that's an asymmetric stretch of the CH3 group. The key thing is that for an alkane, sp3 carbon-hydrogen bonds all show stretching just below 3,000 wave numbers. So it's going to turn out that 3,000 wave numbers is the dividing line between aliphatic CH, which means alkane CH, and alkene CH, just above 3,000. And so if the peak is above 3,000, you're going to have double bonds and aromatic rings. If you have peaks below 3,000, then you're going to end up with just alkanes. Now remember, the alkane is the skeleton of an organic molecule. We make the skeleton out of CH single bonds, and then occasionally we throw in an OH or a C double bond or something like that as a functional group. So most times you're going to see peaks below 3,000. If you don't see peaks below 3,000, that's a unique infrared, because that means there aren't any sp3ch bonds in it, or very few. So we normally find things below 3,000. And there's other types of stretches here. There's whatever this one is. That's a rocking motion, basically. And I don't even know what this one is. That's a bending motion from the CH3. And then down here, there's whatever that is. A fairly complicated motion. So all these different motions are characteristic of an alkane. And all alkanes are pretty much the same. You get some very weird motions like that for this. This is the 2,3-dimethylbutane. But you pretty much end up with just these same types of motions. Now what happens when we get to a carbon-carbon double bond? Well, when we get to a carbon-carbon double bond, what we see, or we begin to see peaks just above 3,000. This peak is at 3080. And so what you see there is now you're seeing the CH, the sp2ch stretches. The sp2ch stretches are just above 3,000 wave numbers. Now it doesn't matter whether it's a double bond that's part of it, just a double bond, or whether it's an aromatic ring. The CH stretches are usually just above 3,000. So you can see this asymmetric stretch, they say, is at 3080. I think there's another one that's just at 3,000, the symmetric stretch. And then after that, everything else is just alkanes, because you get below 3,000, and there's the rest of your alkane molecule of the hexane. Somewhere in here, the carbon-carbon double bond stretch is. It's at 1,600, but notice its intensity, the amount of dip isn't very much. So it's not a very intense peak by any stretch of the imagination. And sometimes we see it and sometimes we don't. But that's where a carbon-carbon double bond stretch would show up. It's about 1,600. And then we get into all the other types of stretches along the way, the scissoring, and these are all legitimate names. You can see that's called scissoring. And now we don't need to learn these. As a matter of fact, our version of infrared is going to be very simple. But there was a time in the not too distant future, or not too past, that you had to know all these things. And then you get some out of bend things like that, where it's flapping, and we don't need to know these. But when I took spectroscopy as an undergraduate, which was a long time ago, I had to know all of those stupid motions, and I didn't learn them very well. But infrared was much more important than it is now. Okay, carbon-carbon triple bond then. Well, there are two types of carbon-carbon triple bonds. There's what's called an internal alkyne and a terminal alkyne. You'll talk about this in lecture, but the terminal alkyne is the one that has the CH bond at the end. And if you have a C triple bond, CH bond, it shows up very sharp at about 3,300 wave numbers. And that is the stretch. It's a moderate, it has a moderate intensity to it, but it's characterized that it's very sharp when you see that. If you just have a carbon-carbon triple bond, the carbon-carbon triple bond stretch you can see is very weak. It doesn't have a lot of intensity, and it's about 2,100 wave numbers. And then the rest of this stuff is just, there's the, what do they call that? Nothing. It's like a wagging motion. Literally from the dog tail wagging. So we got all these different motions for triple bond. Benzene ring. Well, when you have a benzene ring, it turns out that the CH, because a benzene ring is made up of a carbon-carbon double bonds, the CH stretch is just about 3,000. And so you'll see, you really can't tell the difference between a benzene ring and a carbon-carbon double bond. But at least you can tell that the molecule has a double bond or has a benzene ring from infrared. And so we see that. Sometimes we see these three little guys right here. Those are overtones from some other stretches, but they tend to show up when we have a benzene ring. And then some of the other stretches actually occur down in the lower 700 regions, the flying motion of the benzene ring. We're going to use those frequencies later on in the semester, because it turns out that that frequency of the flying actually will change depending on the substitution pattern around the benzene ring. So if two groups are 1,4 versus 1,3 versus 1,2, or 1,2,3 versus 1,2,4 versus 1,3,5, those different substitution patterns give a different set of absorbances down in that 1,000 to 700 region. And so we can actually tell the substitution pattern of a benzene ring by looking at that infrared region. And so we'll do a couple of experiments with that this semester. So that turns out to be a fairly important stretching region as well. All right, we only got a couple left. Alcohols. The big characteristic alcohol is the OH stretch that occurs at 33 to 34 to 3,500 wave numbers. Now we saw water, its OH stretch was about there as well. It turns out that it doesn't matter what the alcohol is. It could be methanol, it could be a 100 carbon chain with an OH on it. That OH is always in that 34 to 3,600 region. And that's the beauty of infrared. Infrared is not specific to individual structures. In other words, an alcohol shows up in the same place regardless of the rest of the structure. Now that's good because it allows us to generalize and say, okay, that's where my OH is, but it's not so good when I try and figure out if it is really methanol or ethanol. So that's why we just use the infrared to say, is there an OH present? If there is, it'll show up between 34 and 35 or 3600. And there's a chart at the end of this that summarizes all those frequencies. Okay, so that's where the OH. Notice it's intense and it's broad because of all the hydrogen bonding that goes on. If you were in my lab last semester, if you remember, for the last 2 experiments that we did where we converted the alcohol to the alkyl halides, we did a quick check using the infrared to see if there was any alcohol left in the molecule. We were looking for that OH peak at 35 to 3600. So we can use this as a test to make sure there's no water, there's no OH in the sample. The rest of this, though, is exactly the same. For this hexanol, what's below 3000? All the alkane CH stretches. Amines with the NH groups, amines tend to be less intense. They're very close to 34, 3500, but they're much less intense. And it turns out that the important one to remember for an amine is that if you have an NH2, you get a little doublet pair in the 34, 3500 wave number region, like this. And that comes about because there's an asymmetric stretch and there's a symmetric stretch of the NH2 group. And so in this case, when you see a little doublet pair like you see here, that indicates that you have an NH2. Now, one of the reasons why I gave you all these example spectra is because you have a stack of spectra that you're going to match the compound to the spectrum for homework. And it might be helpful to go through and kind of look at these particular shapes because you may find, in the homework problems, you may find a spectrum that has that little doublet pair. Well, if it has that, then it is most likely the NH2. Okay? So you're going to want to look over these spectra as you go through the homework. But there's the asymmetric stretch, there's the symmetric stretch. Then there's bending and everything else. Okay, what I think is the last group, carbonyls. The CO double bond has a very characteristic stretch. It occurs between 16 and 1800 wave numbers is where carbonyls show up. Now, there's all sorts of carbonyl functional groups. There are aldehydes, ketones, carboxylic acids. There are literally books that have tables as to what peak frequency corresponds to what functional group, whether aldehydes show up in this narrow region and ketones show up in this narrow region. All we're going to do is say if you see a stronger peak from 16 to 1800, that indicates that there's a carbonyl present. So it won't tell us whether it's an aldehyde. It won't tell us whether it's a ketone. It'll just tell us there's a carbonyl present. And that's all we need to know. Then the final one is a carboxylic acid. You can, for the carboxylic acid, then carboxylic acid has a C double bond O and an OH. But it turns out that the carboxylic acid peak is shifted because the OH is actually hydrogen bonded. Carboxylic acid's like the hydrogen bond in this sort of what's called dimer rearrangement. And so in that case, the peak gets shifted down towards 3,000. And what you end up seeing is you end up seeing sort of the OH peak run into the alkane. You still see the carbonyl at 1,700 here, but you also see then the OH shifted down. So carboxylic acids tend to have this general appearance, and I would bet that somewhere in the homework set there's going to be a spectrum that also has this general appearance, and that's going to tell you it's a carboxylic acid. Flush. So that's those different frequencies. So you have copies then of all of these, and actually because I'm going to record one of each of the lectures, maybe this morning. If this morning wouldn't have worked out, it still may not, then I'll record either Tuesday afternoon, Tuesday or Thursday or morning or afternoon. I'll put the recorded lecture online, which means all the animations that I just showed you will show up online if you want to go back and review it, like maybe for the final exam. The lectures will all be on the Blackboard site. So if we summarize then all of the infrared region that's important to us, here's what it is. We look for alcohols at 32 to 3600. They tend to be strong, broad peaks. Acids will show up closer to 3000. NHs show up between 33 to 35, but they're medium-sized peaks, with an NH2 being a sort of a double pair. Then peaks above 3000 are double bonded hydrogens. Peaks that are just below 3000 are alkanes. And then carbonyls show up from about 16 to 1800. You won't have to memorize this table on any quizzes and or exams. I will give you this table, which means you just have to know how to interpret the spectrum. So when I look at a spectrum, like here's an example. When I look at this infrared spectrum, what do I see? What? Can you be more specific than a lot of absorption peaks? Well, specifically.
The peak up by the 2000 range is there, really wide, so it should be alcohol.
So it's an OH. So this big broad peak here is an OH. So this molecule has an OH in it. Any peaks above 3000? No. So that means there's no double bonds, no aromatic rings. Any peaks below 3000? Yes. So that means there's alkanes in it. Any carbonyl in this molecule? No. For carbonyls, I look at 16 to 1800. I don't see anything, and so in that case, there's no carbonyls. So what I do is I read the spectrum from left to right. I'll look at it, I'll look for OHs, I'll look above 3000 for alkenes and aromatic systems. I'll look below 3000, but I'm not surprised if there's peaks there because it's an alkane. And then I'll look for carbonyls. And so I'll just take an inventory of what functional groups are there. And this molecule is 2-propanol, that's isopropanol. So it's CH3, CH, OH, and then CH3. So what you have for homework then is you've got a series of spectra, and you have a series of compounds. And what you're going to do is you're going to match the spectrum to the compound. And you're just going to hand in the front page, and so you're going to write the spectrum number next to the compound. There's one for each. So if you see OHs, then there's going to be an OH that has an alkane attached to it. There's going to be an OH that may have an aromatic ring or a double bond to it. And so what you want to do is just go through the spectrum and mark down what's there, and then try and match up the spectra that way. Okay, and so that be your homework. We'll collect that up next week. We'll grade it quick and give it back to you. Now, one last thing about the infrared, and that's the idea of what's called the fingerprint region. Infrared spectra have a fingerprint region that occurs somewhere in the neighborhood of about 1,400 wave numbers on down. The fingerprint region is just that. Every organic molecule has a unique set of peaks, intensity-wise and position-wise, 1,400 and down. And so that fingerprint region can be used to identify a molecule if you do computer matching. So sometimes you'll see infrared used in these forensic shows. Sometimes they'll use it to identify mysterious white powders. You can put the white powder onto a infrared and get its infrared spectrum, and then try and match that spectrum up with other authentic samples of white powders that you might have lying around the lab, so that you can say, oh, well, that's cocaine, or that's baking powder, or that's anthrax. Although I don't think anthrax would actually have a unique infrared spectrum, but I think somebody mailed a whole bunch of envelopes containing a mysterious white powder to the New York Times or somebody yesterday, and so I'm sure infrareds have been used to try and figure out what that powder is. But you can use that to compare to unknowns. And the other place that they use it is in the identification of fibers from clothing, or I had to do this for the football field over the summer, because apparently football fields in the spring there was this big concern that they were full of lead, and the ones that were full of lead were ones that were made of nylon, and so they couldn't find the receipt that they had when they bought the football field, so they didn't know whether it was nylon or polyethylene. And that was easy enough to just grab a handful of green stuff from the field, put it on the infrared, and determine whether it looked like polyethylene or looked like whether it was nylon. Basically, if there was a carbonyl, it would be nylon. If there's no carbonyl, polyethylene. Plus, I took a Ziploc baggie, which is polyethylene, and compared it to it, and it was fine. So it's not full of lead. Well, it has some lead in it, but nothing to be concerned about. The 1-inch gap at the midfield, it's huge, and all the black tarry stuff I'd be more concerned about that than the actual field itself. But that's how they use it for fibers. You'll hear, oh, well, you know, this person was wearing a nylon shirt made by, you know, whoever. Well, that's because they're comparing the infrared of the fibers. So that's where it's used a lot more. All right, so that's infrared. Where we're going to use infrared is to figure out whether a functional group is present or not. That's it. That's how we're going to use it this semester. All right, any questions? So next week we will talk about something else, another topic of spectroscopy, probably UV vis.